Okay, so talk to kind of review what we've learned about electricity so far. We know there's two types of electricity. We know electrical charges exert forces on each other. Kind of mentioned that electrical forces are very strong. But now we want to get to just like mathematically, how do we calculate the actual force between two objects, say in newtons? And this was done by Charles Coulomb, 1787. So I did this experiment. I drew a picture of it here. There's a much better picture in the notes that I got from a book. But the basic idea, let's say this marker was being suspended by like a cable, like a thin cable. And what would happen if I twisted this marker and just left it? Well, it's going to twist back. There would be this restoring torque. So if you try to twist the cable, if you actually twisted the cable, it's going to try and twist back. And so that's kind of the idea behind this experiment that he did. So we've got two charged objects. So here we've got this, one of these charges, we'll call it Q1, is attached to some rod which is suspended by a cable. So that's this. And Q2 is attached to a fixed rod. So Q2 is not going to move. Now if we look at a top view, I'll draw that over here. So we've got this Q1, which is attached to this rod. And it's in some orientation. There's no rotation happening right now. But then let's say we bring charge Q2. And say they're repelled from each other. Q2 is not going anywhere. Q1 is going to rotate. But it's only going to rotate so far because Q2 is causing a counterclockwise torque, but the twisting of the table causes a clockwise torque. Now the other end of this cable is attached to a knob that you can twist and apply a torque to the knob to kind of set this right again. So what Coulomb would do is he'd have Q1 here. He'd put Q2 down here next to Q1. Oh yeah, the top view, so they're right next to each other. This is suspended here. And so this would rotate. And then he would apply a torque to this knob to rotate it back to its original orientation. And the stronger the force, the more torque he would have to apply. And so he did several experiments by looking at different factors, like changing the charges, changing the distance between them. And when he discovered the electrical force between them is proportional to the product of the charges, Q1 and Q2. So again, just as an example, say Q1 is 1 Coulomb and Q2 is 4 coulombs. There's a certain force between these two objects. Now it turns out this would be a very large force. I should change these to microcoulombs to be more realistic. Okay, now again, if you look at a separate case where say you have Q1 and Q2, say they're both 2 microcoulombs, the force would be the same in both of these cases, provided the distance is the same. Because here the product is 4 microcoulombs squared, here the product is 4 microcoulombs squared. So it doesn't really matter which object the charge is on, it depends on the product of their charges. And this force also depends on distance. Kind of as expected, the force gets weaker the farther apart the charges. But precisely how it does that, we can also say that the force is inversely proportional to the distance between them squared. So let's say the distance between them is r, then the force is inversely proportional to r squared. Now this might look familiar because we can combine this into a single relation. So the force is proportional to Q1, Q2 over r squared. Now, but what we want is a force in newtons. And so to turn this into an equation and get our force in newtons, all we need is a constant. And again, basically you could do experiments like this to determine the constant. I'll erase everything and just write the result. So a force between these charges call this Ke for like an electric constant. We use K for like a spring constant is K. So just to distinguish it, we're talking about electricity. So we have Ke, where Ke is 9 times 10 to the 9th Newton meters squared over Coulomb squared. So that's a very large number. Okay, now again, I said this might look familiar to you. This is mathematically, this is identical to the gravitational force, where charges take the place of masses, and again, distance is just distance, same as before. Just by way of comparison, the gravitational constant is 6.67 times 10 to the minus 11. And so gravity is an incredibly weak force. Electric forces are extremely strong by comparison. The key difference, though, is as far as mass is concerned, as far as mass is concerned, there's only one type of matter. Everything has mass. We don't have like positive mass and negative mass. Although I think there are some theories that negative mass would be possible. Very interesting if that was the case. I think we'd actually be able to build actual warp drives if that was the case. But we have no idea if that's, as far as we know, there's no such thing as negative matter. So there's only one type of mass, and that's what makes gravity so significant. Because you can have a large accumulation of matter, and it just adds up. The more matter you have, the stronger the gravitational force that it's going to exert on other objects. Right, it doesn't happen with charges. The more charge you accumulate, well, I mean, you pretty much have to apply positive and negative charges equally. You can't have that much of an unbalance, and we will see why soon. We're going to go over into this kind of an interesting example, just how strong electric forces are. And so that's why this relative force, just if you consider two charges, two masses, the electrical force is enormously stronger. It's like a factor of 10 to the 20 difference between them. So 10 to the 20, that's about 100 billion times as strong. But again, charges come in two types. Kind of just an interesting thing to think about. What if there was like another force that was kind of like electricity, but it was as weak as gravity? So gravity is only noticeable because you can have large accumulations. What if there was like another force that had two types, but it was so weak we just didn't even notice it? But maybe that could have some consequences that we just don't notice yet. But yeah, as far as we know, there's only 4 forces. But anyways, so this is the force between two charged objects. Now, this is this constant here. I call it Coulomb's constant. I'm probably not the only one that calls it that, but I don't know if the book does. Anyways, that's Coulomb's constant. It's often written in a different way, and we'll see why later. You might see force written this way. So basically the same thing, except we have a different constant. The constant in this case, instead of Ke, we have 1 over 4 pi epsilon naught. What is this epsilon naught thing? This is, I'll write it here. It's this number, 8.85 times 10 to the minus 12. Now again, why would we have something like this as our constant? We'll see later that there's an equivalent way of writing Coulomb's law, something equivalent to it called Gauss's law, where if we're going to work with Gauss's law, epsilon naught is a more important constant. If we write Coulomb's law in this form, Ke is more important. So again, it's just whichever, depending on which version you're using, that's why we have two constants. We don't need both, because if you know Ke, like we can see Ke is 1 over 4 pi epsilon naught. So we could get by with just one of these constants, but it's worth having both. And again, these are both on the equation sheet. So it's kind of like having two gas constants. One, if you're using the version of the ideal gas law, where you have the number of particles, and then another one if you have the number of moles. So again, we don't need both of those, it's just convenient. Okay, now we're not quite done talking about forces because of a couple things. One, forces are vectors. So this is the magnitude of the force. Now I always write it this way. I should probably do this though. Don't have to worry about r squared because that's automatically going to be positive. But we want, I don't write it this way normally because you just know that these are magnitudes we're talking about. Now these forces have a direction as well. So let's look at an actual example. Let's say we have an xy plane. And say we have one charge at the origin. Let's say we have a positive charge here. And let's say we have a negative charge at some random point here. So what is the direction of the force on, say, this negative charge? Well, there's a line connecting them. And the force is going to be along that line. And again, the negative charge is attracted to the positive charge. So the force on the negative charge would be in that direction. So this would basically depend on geometry. We need to know the coordinates of this point. We have a triangle here. If we know the coordinates of these points, that one's 0, 0, that's whatever it is. We could find the angle. We could break this force into components if we like. But basically the direction is towards a positive charge because they're attracted to each other. Now, force on the positive charge is going to be towards the negative. You might notice that Newton's third law applies here. If A exerts a force on B, B exerts a force on A. And again, it doesn't matter, the force depends on the product of the charges. So the force on each charge, like the force on, say, A, let's say this is charge A. This is charge B. The force on charge A is going to be equal in magnitude to charge B, but they're opposite directions. So here, let's call this FBA. The force on B due to A. And this one is FAB, the force on A due to B. And they cancel each other out overall. If you add these two forces, they are 0 because they're equal magnitude, opposite directions. So generally the force, I write it this way. Just magnitude, the direction, it's nice to just draw a picture and just look at whether they're attracted to or repelled from each other to get the direction. But we can be precise with it, like we know the coordinates of charge B. So we could figure out these angles. And, if we wanted to, we could break that force into components. But another thing we want to consider, what if we had 3 charges? So how does that work? Let me draw that. Let's say we have Q1. Say Q2 is negative. And say Q3 over here, let's make that positive. I'm going to draw this triangle. And let's say we want to know a force on Q3. How do we do that? Now, it's governed by something, it's a big word, but pretty simple concept. Something called linear superposition. I'm not sure why it has such an impressive sounding name, but basically if we want to know the force on Q3, on charge 3, pretend Q2 doesn't exist for a moment. So there's a force, Q1 is exerting a force on Q3. Let's call that F31. That's in that direction. Okay, and now pretend Q1 doesn't exist, and Q2 is exerting a force on Q3. What direction is that? Well, that's here. This is F, the force on 3 due to 2. And so again, basically you have, you calculate F31 and F32 independently. And then you add those. So we can say the force on 3 is equal to F31 plus F32. And that's linear superposition. And again, you can apply that to any of these charges and calculate them. Now, one thing, charges do not exert forces on themselves. So, like charge 3, it's being acted on by these 2 other charges, so they'll each exert a force, and you just calculate them as if they're the only 2 charges in existence, and then you add the result as vectors. So that's the idea of linear superposition. Just calculate the forces independently, add them all up at the end. And I think what I'm going to do is I'm going to, the principle, and again, this would work no matter how many charges. You could have 1,000 charges. Like say we added Q4 over here, then we'd have, the force on 3 would be F31 plus F32 plus F34. However many charges you add. So in principle, we don't know how to find the magnitude of the force using Coulomb's law. So again, we have to know where the charges are, and we need to know what the charges are, like Q1, Q2, and Q3. And then we can calculate the magnitude of the force. The direction is determined by geometry. Again, if you know where they are, you know what directions these lines are that connect them, and so you know what directions the forces are. You don't want to forget to take into account the, the direction, like towards or away from the charge that's causing the force. And so theoretically, let's say we calculate F31 and F32, and then we'd calculate the force on charge 3 overall. So in principle, this is just a straightforward procedure. In practice, there's a lot of work to do here. Especially in a case like this, where we have these forces are in different directions. Now, we are going to confine ourselves to 1 or 2-dimensional problems in this class. Because what would make things much more complicated, although in theory, or like the procedure is exactly the same, like the steps would be the same, but what if we had a charge that was over here, like not on the board, then we'd have forces going into or out of the board, and that just it's a lot more difficult to deal with mathematically, because how do you even define a direction in like when we're dealing with 3 dimensions? You need like 2 angles or something now. And we're not going to get into those kind of complications. So again, the physics is exactly the same. we do the exact same steps, but just the math is a bit more complicated. So we're going to confine ourselves to either one or two-dimensional problems. Now what I'm going to do, I'm going to do a one-dimensional problem, and I think I have a sample problem which I'm going to do as well. Okay, so for this lecture, we're going to do this, a couple sample problems. One, I want to kind of give you an idea of just how strong electrical forces are. So I'm going to do a problem just looking at like the magnitude of force, and then I'm going to do a one-dimensional problem. And then I think I'm going to stop there, but I'll record another video just doing a two-dimensional problem, because there's a lot more steps in that. So I want to have one worked example, so you can always look back. I'll do that in a separate video because it'll take longer. So I'm going to start out by looking at sample problem where, say we have an old penny. Which is 3.1 grams of copper. Now, I had to say an old penny because most nowadays pennies are not made out of copper. And the reason why is pennies really only have one practical use. The only time you ever see someone use a penny is to give to a cashier so that they don't give you more pennies back. You always want to round up to the nearest nickel or something. That's the only use they have, is to keep you from getting more of them. And so we're not going to waste a valuable metal to make something that's completely worthless. Pennies used to be worth something before like the massive inflation. Now they're made out of zinc with, I think, like a tiny, really thin, like copper coating maybe. But in the old days, they were actually made out of copper. Oh yeah, pennies are worth way more than the zinc that they're made out of as well. There's definitely been talk of getting rid of them, but the company that makes them keeps lobbying to keep them in circulation. So, yeah, they haven't gotten rid of them yet. But anyways, say we have an old penny, which is 3.1 grams of copper. And what we're going to do is we're going to have our penny here, and we're going to remove all the electrons from it. Now, you might ask, how are we going to do that? Don't worry about that. It wouldn't be something we could actually do. Well, let's just say we took all the electrons out of them, and we placed them in a container that was 1 meter away from the penny. And the question is, what is the force of attraction between these electrons that we remove from the penny and what's left of the penny? Now, obviously, you're probably thinking this is a stupid problem. And you're right, because the idea of removing all the electrons from a penny, in the first case, that's simply not going to happen. You will not be able to do that. Second, how are we going to put them in this container if they all repel each other? The force involved, forget about it. Not going to happen. Same if we removed all the electrons, this penny would be nothing but positive charge. What's going to hold that together? We're going to ignore all of those issues and just say that we pulled this off somehow. Okay, so in a sense, the problem is kind of straightforward. I'm going to write down the basic equation again, Coulomb's law. Okay, so there's Coulomb's law. And so basically we have two charged objects separated by a known distance of 1 meter. So it's kind of straightforward so far. I'm going to write it like this. Okay. So I'm writing it KEQ squared. Why Q squared? Well, so we're removed all the electrons. So what's left of the penny is going to have a charge of Q, and this container with all the electrons is going to have a charge minus Q. So remember, we had a neutral penny before, so the total charge is 0. And so whatever we took, however many electrons we took out, like whatever negative charge we build up here, that leaves an identical positive charge on the other side. So, and again, we don't care about this minus sign. That just tells us one's positive, one's negative. It's an attractive force. For the magnitude, we don't put that minus sign in there. So we just have KEQ squared divided by the distance, which is 1 meter. So the question is, what is Q? And to start out with, we can say Q is equal to NE, where N is the number of electrons, say. You can also say it's the number of protons. Again, it was a neutral penny, so those numbers are equal. Let's say N is number of electrons. Or let's just say, we'll go with that. Now, I do want to look at a periodic table. I think I have one. So I keep forgetting if copper is 27 or 29 on the periodic table. So I do want to get that part right. Let's see, copper is 29. Okay, so for copper, Z equals 29. So Z is the atomic number. That's the number of protons in the atom. Now, the atomic mass, I'll just write that as M. That is, for copper, 63.54. So basically, we've got like 29 protons and like 34, 35 neutrons, depending on which atom you pick, different isotopes. Okay, so what we have to do now, I'm also going to write down E. So now we know what E is. We have to find out what N is, which is the number of electrons. So first, what we're going to do is we want to find the number of atoms, first of all. And so we have, let's do that first. The number of atoms, I'll call that N with a lowercase a. Because remember, Na is Avogadro's number. I will write that down as well. So this kind of ties into what we were doing before. So that's an N with a capital A for Avogadro. That's what that is. So here, I'm going to spell it out just so there's no confusion. So the number of atoms, we have 6.3 grams of copper. And again, because of the atomic mass, we know 1 mole has an atomic mass of 63.54 grams. And then to get the number of particles, sorry, I do that sometimes. It's 6.02 times 10 to the positive 23rd per mole. So the number of atoms, we have 6.3 times 6.02 divided by 63.54, and then times this very large number. That's going to be around 0.5 times 10 to the 23rd, or 5 times 10 to the 22nd. So again, 6 times 6 is 36. This is going to be a little bigger. And 36 is about, I think this number is a little off. I'm going to look it up. Yeah, that was a bit off. It's more like 3. So I've got this from the notes. 2.94 times 10 to the 22nd. Okay, so that's the number of atoms. Now, the number of electrons, well, there's 29 electrons per atom. So we'd have 29 times the number of atoms, and that's going to be 1.36. Oh wait, sorry, that's the wrong number. I didn't have that in the notes. But let's just say like, 29 times 2.94, that's going to be around 81. So that'd be the number of electrons. And let's just say 80. So if you just do 29 times 3, oh, sorry. Okay, if we do 29 times 3, that would be 87. We're a little bit less than that. Let's say around 85. Close enough. Okay, so that'd be the number of electrons, and then Q is N times E. So we'd have around 85 times 10 to the 22nd times 1.6 times 10 to the minus 19th coulombs. So Q 85 times 1.6. I've got this one written down. I'm just going to look it up. This is around 1.36 times 10 to the 5th power coulombs. So those electrons that we removed and put in this container, that container would have a total charge of minus 1.36 times 10 to the 5th coulombs. What's left of the penny would have positive, that same number in coulombs. Now, I'm going to write this down here and then erase the board. So again, just to review how we got that. The number of atoms, that was like in the previous section. We use this idea of Avogadro's number and moles. We have, say, pure copper. I wrote this down wrong. That's why that number was so wrong. I don't know what I did there. I initially had a bigger number here, and then looked at the notes. I wrote that number down wrong. We had 3 grams of copper, 3.1 grams. And then we looked up the atomic mass of copper to get the number of moles, and then use Avogadro's number to get the number of atoms. So if we have 3.1 grams of copper, we know how many atoms we have. And because copper is 29 in the periodic table, that would mean every atom has 29 protons and 29 electrons. So the number of protons or the number of electrons would be 29 times the number of atoms, and we got a number there. So that's like the number of, say, electrons in this container. So the charge on that container would be the number of electrons times the charge of an electron. So we have Q, and I'm going to erase this. I'll just erase this stuff. Now it's simply a matter of plugging into Coulomb's law. So we have 9 times 10 to the 9th Newton meter squared over Coulomb squared. There, we're dividing by a meter squared. And then we have Q squared, which is 1.36 times 10 to the 5th power coulombs. And that is squared. Now, looking at the units, meters cancel. Coulomb squared, here we have a coulomb, but it's, it's being squared. Everything here. So like when you have multiple things in parentheses like this, we have 1.36 squared times 10 to the 5th squared times Coulomb squared. I guess you could say divided by 1 squared if you wanted. So numerically what we have 9 times 1.36 squared times 10 to the 19th power in newtons. So where did that 10 to the 19th come from? Where did all this come from? Okay, so we took care of the 9, and then I jumped to the 1.36. That's in parentheses to that exponent of 2, so we square that. Now we have 10 to the 9th, and again, this is in parentheses, that this is being squared, so 10 to the 5th squared is 10 to the 10th, and 10 to the 10th times 10 to the 9th is 10 to the 19th. And so our final answer, if we square this, multiply by 9, what we get is a force of about 1.7 times 10 to the 20th power newtons. Okay, that looks like a pretty big force. Now, to try to make some sense out of how big that force actually is, the weight of the Sears Tower, or that's now called the Willis Tower, I guess, so in Chicago. For a time, this was the tallest building in the world. It's still one of the tallest, almost a quarter of a mile high. The thing is huge. The weight of this thing is around 2 times 10 to the 9th power newtons. So if you wanted to lift up this tower, this is how much force you'd have to apply to overcome gravity. Compare that to the force between these two objects. It's basically this is about 100 billion times as much as the weight of this tower. One of the biggest towers in the world. So if you could apply this much force, you could lift, 100 billion of those towers. And that's why this situation is completely impossible. There's no way you could pull them apart in the first place. And if you're trying to find the force just of repulsion between the electrons in that little container, it'd be much higher than even this number. Because the force depends on the distance. If you try to cram them all into something the size of a penny, for instance, the force is going to be much higher than this. So this problem is completely impossible. I guess that's what makes this an interesting problem, to see just why that's impossible to do something like this. Because there's no way you could apply forces like this to separate the charges in the first place and also hold them together. And again, this is kind of why why objects tend to be neutral. It's hard to acquire a significant charge on an object, because say you were able to pull this off, what's going to happen is they're going to come back together very, very quickly. There's nothing that could actually hold them apart. There's no way you're going to apply that much force to hold them apart. So even if you could separate them initially, they're coming back together. Nothing you can do about that. Okay. Now, I mentioned I was going to do 2 problems. I lied. I'm just going to do this one now. But what I'm going to do is I'm going to actually record 2 separate videos. I think this is a good length and a good stopping point. So I'm going to record 2 more videos on this topic. One is going to be a one-dimensional problem, just calculating electric forces between objects. And then I will do a 2-dimensional problem. I'll do those on separate videos. So there'll be 2 more videos like in this module. But yeah, I think this is a good stopping point for now.